All right, everyone, welcome back. And if you remember, in our last section, we did kind of a brief overview of turf fertilization, really because I was going to get into it a little bit more in depth in this one. I felt like the last discussion, I just wanted to kind of breeze over more of the equipment side of it and practices and some tips and tidbits, things like that, just about fertilization, chemical applications in general. This one, we're really going to get into the nuts and bolts of turfgrass fertility. So this is probably, professionally what I spend most of my time, in my career doing and focusing on is fertilization, fertility, soil analysis, and coming up creating programs, agronomic programs for clients all around. And so, hopefully I won't get too long-winded in this, and I'll try and stay on point as much as I can and get through this. And it's a lot of information to go over, but hopefully I'll keep it short and sweet and easy here for you guys to understand. So when we talk about turfgrass fertility, we're going to get into a discussion about fertilizer in general. When we're talking about turfgrass fertility, we're basically focusing on fertilizer and plant nutrient requirements. So just like any living thing, turfgrass has basic minimum requirements that need to be met in order for it to grow properly and maintain overall health. And if they're not met, then we're going to have problems. And as a plant pathologist, I will tell you that I typically tell people, and in most circumstances, in my opinion, many of the problems that we see in turf management, many of the problems we see in turf health and vigor, when it comes to diseases, insects, things like that, a lot of times these are secondary problems. It's more of a symptom than a problem. And in life in general, do we want to treat symptoms or do we want to cure the disease? So it's always good to get back to the big picture when it comes to turfgrass health and make sure before we start trying to go and take a shotgun approach to dealing with problems that we're addressing the overall nutritional health and well-being of the turf. So how do we determine what grass needs? Well, basically, this is done through both soil and tissue analysis. And plant availability is determined by soil testing. So what the plant actually takes up, what the plant's actually using, or what percentage of a nutrient is necessary for a plant to be considered healthy. We typically rely on tissue analysis and figuring out the percentage of these various nutrient, in the plant tissue itself. When we're talking about what's actually available, meaning what do we need to supply the plant with, that's going to come from soil testing. So tissue analysis will tell us what the plant is actually receiving, or what the plant actually, what percentage of nutrient is in the actual plant itself. And the soil test is going to tell us what that soil is actually capable of providing the soil with, and what we are going to need to maybe fill the gap with when it comes to developing a fertility program. So when we talk about nutrients, let's get some nuts and bolts terms down here. We're basically talking about things in the form of molecules, cations, and anions. So soil chemistry 101, molecules, cations, and anions. So when we talk about molecules in general, these are basically where your atoms combine together to form a basic component in chemistry. So most of the nutrients, when we're talking about nutrients, they are going to be in some sort of molecular form in the soil. However, the plant isn't necessarily, when we look at the nutrient component for a plant, how the plant's actually taking that nutrient in, we're actually going to be focusing on the ions themselves. So when we talk about molecules, there's a couple of different types of bonds when it comes to molecules. One would be called a covalent bond. This would basically be where atoms in a given substance, given molecule, are sharing electrons. And these typically will stay complete in solution. So a perfect example, obviously, would be water. Water has a covalent bond. The atoms are shared between the hydrogen and oxygen atoms. And water obviously is a in solution, water is water. But a good example of something going into solution in water would be sugar. So when we dissolve sugar in water, if you're going to make Kool-Aid or lemonade or something like that, you all know that when you dump sugar in water, what happens? It dissolves. The solution remains clear, but you know the sugar is there. If you were to taste that water, you can certainly taste the sugar in the water. Now, that sugar, for that reason exactly, if you think about sugar, if you were to take dry sugar and put it in your mouth, it tastes like sugar. If you were to put sugar in a glass of water and dissolve it, if you drank that water, what would happen? You would still taste what? Sugar, okay? So the sugar is still staying in that solution. It is not breaking apart into carbon atoms and hydrogen atoms and oxygen atoms. It is staying as a sugar molecule in that water. So it's dissolving down to its basic molecular, individual molecular structure, but that basic molecular structure of sugar is staying intact in the water. Okay. There's another kind of molecule. This one works a little bit differently. It's called an ionic bond. Okay, so ionically bonded molecules, basically you have one atom in the compound borrowing an electron and or taking an electron, and you have another atom in that compound that is donating the electrons. So one is sharing it, one is borrowing it. A good example of an ionic compound would be salt, table salt, sodium chloride. So if you know, if you've had basic chemistry, you know that when you put salt in water, when you dissolve it in a solution, put it in water, that sodium and that chloride ion actually will split apart. Now you can still detect the salt. You can perceive the salt in the water, but you're actually perceiving it in its ionic form, not in its molecular form. If you were to evaporate all that water, then basically what would happen is that salt, well, the bonds would continue to repair. The ions, the individual ions would come back together. And if you completely evaporated all the water out of that glass of salt water, eventually you would end up with pure salt in the bottom of the cup. So once you evaporate the water out of that, it is going to be back in its molecular form as sodium chloride. So when we talk about ions, there's two types of ions. So like I said, one is giving the electrons up, one is taking the electrons in. So the one that gives the electrons up, as you would imagine, is going to end up with an overall net positive charge. And these would be called cations. On the opposite side, the one that is borrowing or taking the electron up is going to have an overall net negative charge, and that is what we would call an anion. When we talk about soil fertility, we're basically dealing, again, we're going to be talking about anions and cations. Most of the nutrients that a plant uses are actually going to be in a cationic form, so a positive charge. many of the things a plant is using are going to be in that form. It's not that it's not taking anions up. It's just the majority of nutrients, when we focus on nutrition and soil health and everything, most of the nutrients that the plant utilizes are going to be in a positive charge or cationic form. So there's also two different types of nutrients when we talk about nutrients for plants and for turf. We have your macronutrients and we have your micronutrients. So the macronutrients, when we talk about a macronutrient, we're talking about things that are inside the plant in numbers greater than 1,000 parts per million. So anything that is going to be in a plant, found percentage-wise in that plant greater than 1,000 parts per million, we consider a macronutrient. So what are the basic macronutrients and what do they do? Well, the biggest one, probably the one that's probably in the most abundance inside the plant, is going to be carbon. Carbon is the basic building block of all organic molecules. It's the basic building block of all life on Earth. The plant is getting it from CO2. That's the primary way that it's getting carbon, and CO2 obviously is carbon dioxide from the atmosphere. And it can also get it in the form of low molecular weight amino acids and other organic compounds, sugars, polysaccharides, things like that are present in the soil. But for all intensive purposes, the vast majority of carbon inside a plant comes to the plant in the form of carbon dioxide. Interestingly, plants like turfgrass grow close to the ground so that they can capture the CO2 that's generated by microorganisms in the soil. So, historically, the air hasn't actually always contained enough CO2 for plants to passively absorb it through the air. So, when we talk about rising CO2 levels in the atmosphere and things like that, that's a relatively unique phenomena. We don't always see that. If you look at the Earth's geologic record, we haven't always had periods where we have CO2 levels this high. We've had many periods, frankly, where we've had CO2 levels on Earth much, much higher. But ever since the great oxygenation event, the CO2 levels on Earth have been much lower, though they have at periods in time been higher than they are presently today. But it's kind of a unique thing. When we think about plants, we think about them just passively taking in carbon dioxide from the atmosphere. But if you really look at trees, when you look at shrubs, plants in general, and turfgrass is no exception, when you look at their overall shape of their canopies and everything, and you consider that umbrella type form, it's really interesting that, when you think about this, that they're actually trying to catch that carbon dioxide as it's being given off by microorganisms in the soil, and as it's being released into the atmosphere, they're trying to take advantage of the fact that that carbon dioxide is being released in the soil. And grasses are no exception. They actually evolved to take advantage of CO2 escaping from the soil. That's why they actually grow so closely to the soil. If you think about going all the way back to the beginning modules of this class, when we talked about the Ice Age and the Quaternary Ice Age period, and how we had this rise of turfgrass on Earth, or grasses in general on Earth, as a result of ice ages. That's one of the things that was unique to the ice ages, is the CO2 levels were actually much, much lower than they are today. So, the ice ages basically, and that lack of CO2 in the atmosphere meant that it was more difficult for plants to take in CO2. And so grasses were able to adapt and spread so quickly over Earth, partly because they're by their design, they're kind of growing close to the Earth and taking advantage of that CO2 escaping from the soil from microbial degradation. So, what is the effect of atmospheric CO2 concentration on plant growth? Well, some studies have been done in growth chambers where they can control CO2 release into the environment, and actually maintain that CO2 level at different levels. And you can see that CO2 actually does have a significant effect on the growth of plants. So right now we are actually, I would say, a little bit above average. We're a little bit above 400 parts per billion of CO2 in the atmosphere. And when we talk about the ice ages, we were actually less than 300 parts per billion CO2 in the atmosphere. So, as you can see, there is a definite response when you look at where CO2 levels were during the ice ages versus where they are presently today. And you can see that effect. And the interesting thing here is, when you look at the grasses in general, you can see that they actually are doing very well, continuing to grow at much, much lower levels of CO2 in the atmosphere. And again, this gets back to what I was saying a moment ago when you talk about turfgrass is actually, being very well adapted to capturing or taking advantage of CO2 escaping from the soil. The other thing, as I said, is again C4 versus C3. So rice being a 3 carbon or C3 cool season plant versus your 4 carbon plants, you can see again how the C4s, again, we remember that they're able to manage carbon dioxide a little bit more efficiently than the C3 plants. So again, we can see, further evidence that the C4 plants really adapted and evolved to take advantage of lower atmospheric CO2 levels. So, again, just a nice little slide that illustrates this here. But you can see the effect that increasing the parts per billion of CO2 in the atmosphere has overall on the growth of plants. So the next one down from carbon, as far as presence in the plant being a macronutrient, would be hydrogen. So hydrogen, again, is part of all the organic molecules. It also plays a critical role inside the plant as far as electron transport for ATP or energy production in the plant. This comes from hydrogen ions in the soil and water taken up by the plant that is split during photosynthesis. So, when we talk about photosynthesis inside of plants, and turf is no different, it's using energy from the sun, and it's using various enzymes and compounds inside the plant to split that water into oxygen and hydrogen. The hydrogen is then used as part of what they call the electron pump mechanism inside the plant, where it's using it to produce energy in the form of ATP. So, very, very critical component to the plant, but, again, widely available to the plant, both in ionic form through the soil, and the primary form obviously would be through water. So the next one down would be oxygen. Oxygen is derived from splitting of the water during photosynthesis. It's coming out of the atmosphere. It's also coming out of, the water as the water is being taken up in the plant. So a couple different ways that the plant is getting oxygen. So again, this is actually during photosynthesis ends up being a waste byproduct of the photosynthesis process. But then again, when the plant is in respiration mode, which usually is occurring at night, then it is actually taking this oxygen back up from the atmosphere and using it again for cellular respiration. So just like us and every other living thing, plants also do take oxygen in and expel carbon dioxide. They just have the added benefit of, as a result of photosynthesis, they are releasing oxygen back into the atmosphere as a waste product during the day. And plants actually, net-wise, plants have a net positive release of oxygen. So that basically means that they're releasing slightly more oxygen into the atmosphere than they're using. So it's not a big difference, but it's enough that basically that process of photosynthesis has resulted over time in a significant reduction in carbon dioxide in the atmosphere and an overall increase of oxygen. So nitrogen would be the next component that's important to plants. This is going to come in two forms. These are both anionic and cationic forms. So this would be one of the anions that we talk about that a plant will take up. The anionic form would be nitrate, and the cationic form would be ammonium. So these are basically coming to the plant from the soil. These are used to make amino acids. The plant also has the ability to take up low molecular weight amino acids and use those instead of having to manufacture them themselves. So 50% of the nitrogen in plants is in the form of a catalyst inside the plant called rubisco. So this is ribulose bisphosphate carboxylase oxygenase. So this is basically a key enzyme or catalyst that's used in glucose formation. So 50% of the nitrogen that a plant takes up and uses actually gets dedicated to this. It's an incredibly inefficient molecule, but it's basically what the plant has available to produce glucose. So as a result, the plant actually produces quite a lot of this rubisco and stockpiles this rubisco in storage vessels all over the plant in order to have it available to use as it needs to. Okay, the next macronutrient that we're going to talk about is phosphorus. This actually, again, is another anion, so negatively charged compound. It comes to the plant in the form of phosphate. Again, in the soil, it's used by the plant to basically maintain nucleic acids like DNA and RNA. It's also a component in many enzymes and catalysts inside the plant. It's also part of the energy storage system, which is adenosine triphosphate, phosphate in the adenosine triphosphate. So that's what the P is for in ATP. It's also a component in the phospholipids, which are used for cell and organelle membranes. So again, phospho, meaning that it's phosphorus derived, so that would be in the form of phosphate coming into the plant, and phosphate would be an anion coming into the plant. So next one is going to be potassium. This is going to be a potassium cation, so positively charged ion in the soil. It's used by the plant primarily as an osmolyte, and it's electrolyte basically. It helps to maintain water balance inside the plant. It helps the plant maintain energy efficiency by facilitating optimal movement of water, sugars, starches. It's also used for some enzyme activations inside the plant to make them work. So basically a key component or the active component or active site on an enzyme to make the enzyme actually work and do what it's supposed to. Next one is going to be calcium. Calcium is, again, a cation, so positively charged. It comes to the plant, again, from the soil. Serves as a secondary osmolyte, so similar to potassium. It's a secondary osmolyte. It's part of the cell wall integrity, so just like the bones in our body, it's part of the structural integrity of the plant. Next one, as far as macronutrients, is going to be magnesium. This is going to come in the form of a magnesium cation. Has a net 2 positive charge, so like calcium, it's a 2+. Magnesium would be a 2+ net positive charge. Again, coming from the soil. This one, it does play an important role in the plant. It is the center of the chlorophyll molecule. So some of you might think that iron, is very important. Iron is very important to grass, in terms of green up and things like that. You might have heard along the way that iron is important to chlorophyll production, but it's not actually part of the chlorophyll molecule. The magnesium cation is actually the nutrient that is primarily that is sits right in the center of the chlorophyll molecule. Magnesium is also important, as again, like potassium or calcium, it activates many enzymes. It's also part of Rubisco, which again, we know that 50% of the nitrogen in the plant goes to be used to make Rubisco. So again, magnesium is another critical component to the plant. With nitrogen, it's being used as part of the Rubisco molecule, which again is the most abundant enzyme in the plant. The next macronutrient in the plant is sulfur. So this is in the form of sulfate. This is another anion, so it's a negatively charged ion. It has a net 2 negative charge. And again, the plant's deriving this from the soil. Its primary role inside the plant is it's a building block in nucleic acids. It's also involved in amino acid synthesis and chlorophyll synthesis, which would be the manufacture, the production of amino acids in chlorophyll. So that would basically wrap up your macronutrients. Again, these are all things that are going to be present inside the plant in concentrations greater than 1,000 parts per million. So now we're going to talk about micronutrients, and there's many, many more of them. These are all necessary for plant growth and development. And they are found in the plant in concentrations less than 100 parts per million. So macronutrients greater than 1,000 parts per million, micronutrients are less than 100 parts per million. So it doesn't take very much of these, but if they're not present, the plant cannot function properly. Another interesting thing is this is not settled science. So the list when it comes to nutrients and primarily micronutrients continues to grow. And the latest one that we've started to look at within the plant is nickel. And I'm sure that as science goes on, we're going to continue to find that there are other nutrients in the soil, other elements that are going to play a role in some way, shape, or form. So just understand that, our understanding continues to evolve when it comes to plant nutrition, and the list isn't complete. Nickel would be one of the newest ones to hit that list. So what are these micronutrients? Well, we'll start with boron. Boron is in the form of the borate. Again, this is another anion. So it has a net 3 negative charge. It's coming to the plant from the soil. Just like most of these are going to come to the plant in the soil, with the exception of carbon, which is primarily coming from the atmosphere, and oxygen, which is primarily, it's coming to some degree from the atmosphere, and then the rest of it's coming from the soil in the form of water. So boron, again, another anion, negatively charged. This one is also part of the cell wall. It also facilitates calcium uptake and is also involved in hormone functions within the plant. It's also a critical component to cellular division or mitosis, and it's also a critical component of cellular or sexual reproduction. So when that plant is basically flowering and producing seed, it is very involved in that process. The next one is going to be chlorine. Chlorine is another anion. It has a 1- charge. This one is coming from the soil. It's involved in stomatal opening and closing for respiration and leaf turgidity, which is basically how stiff or rigid the leaf is. So normally we don't think of chloride as a nutrient. Okay, typically when we think of chloride, we're talking about chloride toxicity, like from salt damage. But it is necessary in small amounts. Usually we don't see deficiencies in it. Very, very seldom do we ever run across a chloride deficiency in a plant. And typically, most of your fertilizers are providing some chloride to the plant in the form of, say, potassium chloride is a common ingredient used to make fertilizer. So we don't typically think about chloride deficiencies in a plant, but it is needed to some level. Too much of it, not a good thing. Next, let's talk about copper. Copper is a 2 plus cation, comes out of the soil. It activates many enzymes involved in metabolism, cellular respiration, and photosynthesis, as well as lignin formation. And so that one again is necessary to the plant. Iron again, we talked about iron earlier when we were talking about magnesium. So iron is a micronutrient where magnesium is a macronutrient. So iron is a micronutrient, comes in the form of a 2 plus or 3 plus cation from the soil. It is primarily involved in chlorophyll synthesis, so that is correct. If you're thinking is iron is necessary for chlorophyll production and the greening of turf, that is right. But we don't need very much of it to do that job. This is something that is recycled pretty efficiently inside the plant, and it's used by the plant to create the chlorophyll molecule. It's also involved in a few other enzymes or catalysts inside the plant. But again, the plant does a pretty good job of recycling iron, and we don't typically need it in very large amounts. So, you can put a ton of iron down. It isn't necessarily going to be, it's not necessarily going to elicit any kind of greening or darkening response if it's already in the soil, present in the soil in adequate levels. Next is going to be manganese. So we often focus on iron, but if we focus on iron, we should also focus on manganese. This is going to be in again a 2 plus cation form coming from the soil. It's basically involved in the splitting of water during photosynthesis and the electron transport during photosynthesis, and it's also involved in chlorophyll synthesis. It's involved in, as part of many of the enzymes involved with lipid formation and nitrate assimilation. So nitrogen being a macronutrient, and one of the forms that nitrogen can be taken up is in the anionic form of nitrate. And so manganese is very essential in order for the plant to be able to take up and assimilate that nitrate. So if we don't have adequate manganese, it can create problems with nitrate toxicity in the plant and overall inability of the plant to effectively use that nitrate that's often comes to the plant in the form of fertilizer. So, again, manganese is very important. Oftentimes when I see iron deficiencies, it's probably pretty safe to assume that we don't have enough manganese present either. So it's not a bad idea if we're going to go and apply iron to also apply manganese, because oftentimes what will happen is if we have an iron deficiency and we apply that iron, then next thing you know, you end up with a manganese deficiency as a result of increasing the iron. So not a bad idea to pair both iron and manganese up. If we have a soil test calling for one or the other, just go ahead and plan on pairing both of them up and putting both of them on the plant at the same time. So next one down is going to be molybdenum. So this is actually going to be in the form of a molybdenate anion. It comes from the soil. This one is also involved in nitrogen assimilation, and the other role that it plays in the plant is with hormone synthesis. So this would be things like your auxins and cytokinins and gibberellins and things like that. So molybdenum is very involved in those processes inside the plant. Next one is going to be zinc. Zinc is available to the plant in a cationic form. It is in the soil, comes to the plant from the soil, is used primarily in chlorophyll production. It also is the active member of many enzymes involved in the conversion of starch to sugar and auxin production for root growth and shoot elongation. So molybdenum plays a role in basically all the hormones inside the plant, but zinc is specifically for auxin synthesis. So interestingly, when we look at root growth on plants, a lot of times you might hear or see something where they talk about zinc being essential for root growth and root development, but really what it's doing is allowing for the conversion of starch to sugar inside those roots, and then it's also involved in the auxin formation, which helps to promote that root growth. Next, we're going to look at nickel. Nickel is a relatively new one. This is, again, a cation in the soil. We didn't really know a lot about it, but we started to find out that nickel is playing a role in the plant. It's not a center role, but it does have some benefit to the plant. It basically helps the plant to convert urea into ammonium to prevent urea toxicity. So when we talk about urea toxicity, sometimes the plant does have urea actually go into the plant. Urea can actually be taken up by the roots in a whole urea molecular form. What can happen when you fertilize a plant is you can end up with an overload of urea inside the plant. So you can end up with urea toxicity. So just like human beings, too much urea inside a human body is not a good thing. It can cause a lot of problems. That's no different for the plant. The plant can over time end up with an accumulation of urea. Nickel plays a very, very critical role to help the plant to manage that urea by converting it into ammonium, which will allow the plant to use that ammonium for other uses in the plant. So the primary form of nitrogen used in lawn care is, again, urea. And can the plant absorb urea? Yes, the urea can actually be taken up in whole molecular form by the plant. And so again, nickel, if we are running nickel deficiencies in the soil, I don't think this is something that's necessarily present on a lot of tests yet. I think you do have to test for it separately. But it can help with, again, when we're talking about fertilizer going down in the form of urea on grass, the nickel could be, something that we want to look at or consider to help us better manage and utilize that fertilizer. It could help with increased fertilizer efficiency, allowing that plant to better convert the urea into ammonium inside the plant, and to help prevent fertilizer burn inside the plant in the form of urea toxicity. So what do plants do with all of this? I mean, what is the point of everything that's going on in the plant? What is all of this getting down to? We know that plants make sugar. Okay, we cover this in basic bio 101. In high school and even grade school for that matter. We know that plants do photosynthesis, and we know that the reason the plants have photosynthesis is that they are producing sugar, okay, in the form of glucose. But what are they really doing? What is the point of all of this? Well, the point is that what plants are really doing is they are synthesizing or manufacturing their own amino acids, okay? So you and I don't have the ability to make amino acids. We have to eat them in the form of plants or animal protein. But at the end of the day, we have to consume proteins to get the amino acids that our bodies need. But plants, they have the ability of manufacturing their own amino acids, and we don't often think about this, but that's really, at the end of the day, the plant isn't really, it's producing sugar, it needs carbohydrates for cellular respiration, but at the end of the day, what is it really doing with all these carbohydrates? It's fixing them with nitrogen, again, coming from urea, coming from ammonium, coming from nitrate. It's taking that nitrogen, and it's fixing it with those sugar molecules and or glucose molecules to create its own amino acids. Okay, so again, we have to eat to get these basic building blocks. Plants don't. Plants have the ability to manufacture all of these amino acids. So, that's kind of the neat thing. And there's 18, what we consider 18 essential L amino acids when we talk about a plant. And there's, I think, a few more with human beings than what we get from plants, but plants actually do, produce all 18 of the amino acids that are necessary or considered essential for life. So now we're going to talk about interpreting a soil test. And, what does this all mean? When, we talked about the macros, the micronutrients. So now let's get into the soil test and talk about what are acceptable ranges when it comes to soil tests. So one of the terms that we're gonna come across when we look at, or a couple of terms that we're going to come across when we look at a soil test, is ppms, or parts per million. And other times we're going to look at a soil test and we might see things interpreted in terms of pounds per acre. So, what are these two and what do they mean? Well, 1 furrow acre slice of soil, which would be about 6.7 inches deep, weighs roughly 2 million pounds. So, what we would call a furrow acre slice, which would be a standard unit of soil when it comes to soil testing, weighs about 2 million pounds. So when we talk about parts per million, and we know that soil, a furrow acre slice of soil, which is basically your root depth of a given body of soil, is 2 million pounds. So a 30 part per million result on a soil test is going to be equal to 70 pounds per acre, and vice versa. So just understand that, a pound per acre reading is double a part per million reading. And now when you look at a soil test, if I have it in terms of parts per million, all I have to do is double that to get the pounds per acre of available nutrient. Or if I'm given the pounds per acre of a given nutrient, I can divide that by 2, and that will give me the parts per million of an available nutrient. So another thing that we want to talk about when we look at soil tests is the concept of exchangeable versus available nutrients. So exchangeable would be the total amount of nutrient that is available. So many soil tests talk about exchangeable, or they provide you results in exchangeable. And this is an important thing to ask and to know or think about when you're soil testing, because what this involves basically is it requires reacting that soil in a lab to force or shock nutrients out. Okay, so when we look at the exchangeable, it's basically saying this is the total amount of nutrient that's available if we chemically react that soil and shake everything out of that soil. This is what comes back on the test. But this doesn't mean that this is actually available or entirely available to the plant. And that's because many of these nutrients might be tied up in a reacted or mineral precipitate form that isn't readily available to the plant. So, when we talk about plant available units versus exchangeable units, available is what is actually able to readily go into solution and readily be taken up by the plant. Okay, so again, there's a difference between the two, and a lot of soil tests only show you the exchangeable result. So what does that mean? It means you can look at that soil test and think, oh, well, I have adequate levels of that nutrient in the soil. Wrong, because those may not necessarily be available. They're exchangeable. In essence, if you chemically do something to the soil, you might be able to make them available, but that's highly unlikely. So what we really want to look at is soil tests that have the ability to show us both the exchangeable and the available nutrients on that test, because the available at the end of the day is what's actually going to be available to the plant to take up. All right. So another thing that we need to talk about when we look at soil testing is, what I call the phosphorus dilemma. So we have an issue going on, and I'm seeing this come up more and more on soil tests. In fact, I was meeting with a customer not that long ago, and they told me that roughly 65% of the soil tests that they run are coming up phosphorus deficient. Okay. And this is because we haven't been putting phosphorus in maintenance fertilizers. As a general rule of thumb, we haven't been putting them in there for about the past 10 to 15 years. So, as you can imagine, if you stop putting something in the plant, and again, this is a macronutrient, so something that's present in the plant in numbers greater than 1,000 parts per million. So what's happening is over time, as you can imagine, the soil is now becoming depleted of phosphorus. And almost every soil test I run across now comes up low in phosphorus. So phosphorus really, at the end of the day, is a red light, green light nutrient. So if it's not there in sufficient levels, the grass will not grow. Okay, and if it's there, it will. If it won't, then the grass isn't going to grow. And this is a perfect example. That, again, this is rice. These are rice paddies, but rice again is a grass, and you can see that when it's available to the plant in the appropriate amounts, then the plant flourishes. But again, if it's not there in sufficient levels, these plants struggle. Okay, and so this was a good study that illustrated that again in rice, but it's no different in turf. So the other thing that I'm starting to see as a plant pathologist is it is a significant contributor of disease and poor performance in lawns. So, whenever I show up in a lawn, if a client calls me and they're like, can you look at a property, and I show up and there's a lot of disease present, or that lawn is just struggling to perform, I almost immediately am going to suspect that there's a phosphorus deficiency. The challenge with phosphorus is that when we look at soil, the adequate level, if we want to talk about what is that red light, green light threshold on an available level on a soil test, it's 35 parts per million or 70 pounds per acre. So if we're below 35 ppm on a soil test, then it's a red light. Okay, if we're above 35 ppm on a soil test, that's a green light. The problem is that if that's great for the soil and that's great for turf and plants in general, but when we talk about bodies of water like Lake Erie or the Chesapeake Bay, this poses a challenge because most of the phosphorus in these water systems is coming from agriculture, but it is also coming from turf and landscape to some degree. The problem is that you only need 50 parts per billion of phosphorus in the water to cause algal blooms in the water. So like these algae blooms that we see in Lake Erie, again, we only need 50 parts per billion of phosphorus in the water. We need significantly more than that in order to adequately supply the needs of plants and the needs of turf. One of the biggest sources that I see contributing to this is, with the increase in agricultural production, I've seen a lot of farms, especially in Northwest Ohio, abandoning no-till practices and going back to conventional tilling, which again is breaking up and opening up that soil, but it's also making it possible for a lot of that soil to get washed away. And phosphorus, it hitchhikes along with soil. It's not like phosphorus is just leaching and going into the waterways. It's hitchhiking along with soil. So anytime you have erosion, you're going to have phosphorus leaching with that soil. So even though it doesn't significantly contribute to the problem, lawn care is considered a luxury, and it will be the one to pay the price. Ironically, one of the best ways to protect the environment is to maintain a healthy lawn, okay? But, the problem is you don't see farmers throwing up billboards along the Ohio Turnpike advertising the fact that they're, contributing to the phosphorus problem, or that they're, putting a ton of nutrients and everything down. They're not advertising what they're doing. Lawn care obviously is. So, because of that increased visibility, and because It's viewed by so many people as a luxury and not necessary. It gets a black eye in all of this because you don't see farmers going out advertising that they're putting pesticides and fertilizers and things down on their fields. Lawn care, unfortunately, does. Okay. So, there's been some really good studies that have been done that do talk about the importance of phosphorus, though, in maintaining adequate health and vigor in the turf to prevent, like what you're seeing in this picture here. When we get these heavy rains at summer, if you don't have a lush, thick green lawn that's really helping to slow the flow of water down and also hold that soil in place to prevent erosion. You're going to have soil erosion, and with it, you're going to have phosphorus going into the storm sewers and eventually making its way into the waterways and into Lake Erie. So there's some other soil factors that impact turf vigor. Another one that's important to talk about in regards to soil testing and plant health is pH. So pH would be the hydrogen ion potential. So this is going to measure the acidity or alkalinity of the soil. Okay. And the reason this is important is because pH is going to affect the availability of many plant nutrients. So the sweet spot, really, when we talk about pH and soil testing, the sweet spot is basically going to be between 6.5 and 7. So slightly acidic on the pH scale, not very much, but basically, just a little bit below a neutral pH or pH of 7. This is what's going to give us the greatest overall availability of nutrients in the soil. So again, 6.5 to 7 is going to be that magic sweet spot to guarantee maximum availability of plant nutrients. We can do things to the soil if the soil doesn't have an ideal pH. We can do things to soil, in essence, shocking the soil to change the pH. Again, remember what I was talking about with the soil test and exchangeable versus available. On a soil test, they shock that soil with strong acids or strong bases to make things available. We can kind of do the same thing in the landscape. We could shock that soil to have a dramatic change. It's a short-lived change, but it's a change nonetheless. It can help us to make things available to the plant. So one of the ways that we will shock soil to change pH is lime. And we will use lime to raise the pH, and depending on the form that we use, we can change that pH either for several months or even years. Calcitic lime is the one that I primarily recommend up here in Northeast Ohio. It's 90% available, which means it's going to get into the soil. It's going to quickly raise that pH, but it's short-lived. It's usually going to only last for about 6 to 9 months. The other form of lime that we see readily used out there is dolomitic lime. This one is only 10% available. It's very slow acting, but it will last up to years once it's present in the soil. So on the other side, we use lime to raise a pH, but on the other side, we actually will use sulfur to lower the pH. Now, this isn't an instantaneous thing. It takes a while. The sulfur has to go through a couple of different chemical processes in the soil in order to acidify or lower the pH of the soil. It doesn't just get dumped out there and turn into like sulfuric acid or something. It's got to go through a couple of steps in that process to actually start to acidify the soil. Again, this isn't very fast acting, but usually if we put an adequate amount of sulfur down to change the pH to the desired level, it's going to take it several months to fully take effect. However, once it does, it's going to maintain that pH for a period of about 5 to 7 years. So another compound that we will often use to lower the pH is ammonium sulfate. So again, sulfur can be used for a long-term change, kind of like dolomitic lime can be used for a long-term change. But if we need to have an effect in the short run, if we maybe we need to go out there and do something that's going to give us a little bit quicker result while we're waiting for that sulfur to kick in, ammonium sulfate is something that we can use to slightly lower the pH. Not going to have a big change, but we can use it in the short run to slightly lower that pH, okay? Another way that we can affect the pH in the soil is organic matter and amino acids. So these don't necessarily change the overall pH in the soil, but what they can help us do is buffer the pH, meaning they're going to help moderate any significant changes in pH. So, once we've done something like a lime or a sulfur where we've started to basically effectively change that pH, over time we can help buffer that pH and keep it from changing too much one way or another by incorporating organic matter or by the addition of amino acids into that soil to help buffer that. Ultimately, the thing to remember when it comes to pH is it's unrealistically to permanently change that pH without taking drastic measures. So, unless you're talking about completely removing that soil and replacing it or something like that, we're really not going to change that soil. Ultimately, whatever that soil test tells us, that's ultimately where that given area of soil is going to end up back. So we can do a lime, we could do a sulfur, but eventually over time, that pH is going to end up right back where it started when you first took the test. It's just the fact of life. So, we're not going to focus on doing anything to drastically change it. We're only going to focus on temporarily changing it in that furrow acre slice, in that root depth, of 6 to 8 inches. That's basically where we're talking about making that change in the root zone. And we're going to have to do it on a periodic or regular basis. This is not going to be a one and done fix. Okay. So when we look at nutrient availability, it's important to talk about CEC. This is the cation exchange capacity of a soil. This measures the soil's ability to attract and retain cations. Remember from our macros and our micros that most of the nutrients that a plant uses are in the form of a cation, a positively charged ion. And one of the ways that the plant, or one of the ways that the soil rather, manages this is through something called the cation exchange capacity. So CEC is not a chemical reaction. It's more like a magnet, okay, or a sponge, if we'll have it. Probably a better analogy would be like a magnet. When we have a high CEC, that means that the soil has more of a magnetic potential to basically attract and retain these cations. So, if you're putting fertilizers and stuff down, CEC is going to be really valuable to you because the higher the CEC of that soil, the more it's going to have the ability to attract and retain those nutrients and keep them from going to other places. So most secondary and micro nutrients are in cationic form. So the macronutrients, we have our primary and secondary. The secondary macros and the micronutrients are pretty much almost all going to be in cationic form. And cations are going to jump off if they find something they like better. So again, it's like a magnet. The magnet can't permanently hold something to it. We have the ability, if we exert enough force, we could pull, whatever that is, if it's a screw or a paper clip or something like that stuck to that magnet. If you exert enough force, you can pull that object off of the magnet. And the CEC is the same way. So it does form a relatively tight bond with those cations. But again, if some other more stronger, more potent reactive force comes along, it has the ability to pull those off, just like pulling that paper clip off that magnet. So when we talk about CEC, we're talking about it, a unit of measure that is in the form of milli equivalents per 100 grams of soil. So when you see the number on a CEC, say it's like 10 or 15 or 100, what we're talking about is it's 10 milliequivalents or MEQs per 100 grams of soil, or 100 MEQs per 100 grams of soil. So this is how we determine the pounds of available nutrient per acre. So without getting too complicated, when we go through and look at a soil test, and where you're trying to figure out, well, how are they coming up with the nutrient recommendations, or how much of an available nutrient? Remember, we look at a soil test and we see exchangeable, but then we use that CEC to calculate the amount of either parts per million or pounds of available nutrient per acre. So the higher the CEC, the more potential for the soil to hold nutrients. So in this game, bigger is better. And it comes mainly from the clay minerals in the soil. So, many of you ran your jar test, and we had clay soils or clay loam soils. So that's not a bad thing when it comes to soil nutrition, because most of the CEC in the soil comes from clay. The individual clay minerals or clay particles are what give us the cation exchange in the soil. So we can also, the other thing that's cool about CEC is we can influence soil bulk density and pore space by filling the CEC with calcium. So, calcium, if you remember, it's a cation. It has a 2+ charge versus, say, sodium, which has a 1+ charge. What that means is that calcium will actually take up twice as many active sites on a clay particle as sodium. And what happens is that'll help us a couple of ways. It'll shake so, say we have a lot of sodium in a soil, we'll shake that sodium off the soil. But the other thing it'll do is it'll actually pull those clay particles together and form larger aggregates in a process called flocculation. So, if you imagine these clay particles are kind of like these flat little crystalline structures, and they tend to lay on top of each other. So when we have a bunch of 1+ cations in a soil, what happens is it ends up flattening or compacting the soil. When we start throwing in these bigger cations, these 2+ cations, which have the ability to take up twice as many sites, it loosens those clay particles up and allows those clay particles to start aggregating together in a process called flocculation. And, that helps us, again, increasing pore space and decreasing the bulk density of a soil. So organic matter also has cation exchange capacity, and it also has the ability to retain anions like phosphate. So if you remember, some of the anions that we talk about, like boron, phosphorus, molybdenum, these, they're not going to bond to clay particles in the soil because they're anions. But if we have organic matter present in the soil, this will help us actually retain these anions, or negatively charged anions. So again, this is a lot of times we look at humates and humic acid in the soil. But another thing that we don't always think about are amino acids. Amino acids, again, we could use them to help buffer the soil, but we can also use them to help us, to have some additional CEC in the soil and to help tie up some of these nutrients. Interestingly, amino acids, again, like fulvic and humic acids, have the ability to retain both anions and cations. So another form would be weathered or oxidized charcoal. We don't want to use activated charcoal. Activated charcoal basically doesn't have enough negatively charged sites on it. It has a lot of positively charged sites on it. So what'll actually happen is you throw it in, it's literally going to start reacting with anything and everything in the soil and end up rendering that soil in essence sterile. So it's great for cleaning things up. If you think about activated charcoal and filters, when we talk about charcoal or carbon going into the soil, we really want to use a weathered or oxidized charcoal, not an activated charcoal. Smaller organic molecules also chelate nutrients in the soil, protecting them from reacting with other minerals. So this is like organic compounds break down the nutrient is made available to the plant. So this is something to think about, that, the organic matter serves as a food source for the microbes in the soil, whether it's bacteria or fungi. It's serving as a food source for those microbes in the soil, and as they break them down, the organic matter will, basically unchelate or release these ions and make them available to the plant. So there's different CECs when we talk about different soil particles and different soil types. Organic soils, for example, tend to have very, very high CECs. They tend to be, in that 50 to 100 MEQs per 100 grams. So, if you had a high organic soil, you would probably see a very, very high number. It can actually sometimes be even higher than 100, but for most purposes, 50 to 100 MEQs is going to be a pretty common number when we're talking about organic soils. Next down again, when we talk about clays and things like that, clay soils or loam soils, you're going to see probably CECs on a soil test in a 30 to 40 range. Clay loams tend to be more in a 15 to 30 range. Silt loams end up tending to be more of a 5 to 15 range. So silt doesn't really have the CEC value that clay does. They're much, much smaller particles than clays. So we don't really see a lot of CEC when we talk about silty soils. So if you're dealing with silty soil, this is something that you're definitely probably going to want to amend and bring in more clays and more organic matter to amend that silty soil to get it into a better CEC. The lowest on the range is going to be sand. Sand has a very, very low CEC, usually only 5 to 10 MEQs versus clay, which is going to be above 30. Silt not quite as bad as sand, but they're pretty much down. Both of them are pretty much down at the bottom. So same thing with sand. If we have a lot of sand, we're probably going to want to amend it with some clay, with some organic matter to get that CEC higher. Okay, so silt in and of itself has no CEC. So this is important to remember that, if you had 100% silt on your soil texture, which you're probably not going to, you're going to mostly see silty soils, which still have some clay in there. Silt in and of itself has zero CEC. So I don't know too many circumstances where we've run into silty soils, but again, as we move more and more in the direction of silt on our soil triangle, your CEC is going to be going lower and lower. Same thing as we move more toward the sand spectrum. So the sweet spot's going to be where we get into more of the clay loams, medium loams, things like that, or moving higher into this clay profile. That's where we're going to see much higher CECs. So let's talk a little bit about lime. I know that when we talked about lime a minute ago, we know that we can change the pH in soil with lime, but there's something when I talk to guys or make recommendations to people about liming, there's some things to know about lime. Okay, so calcium to magnesium ratio and base saturation are really important when we get into liming and lime. So if we're going to look at doing lime, we really want to make sure that we're not just going out there willy-nilly doing it, because we can really mess up a soil if we don't use the right lime and we don't do it properly, or if we're unnecessarily doing. A lot of lawn care companies get into the habit of selling lime applications. Like, why? Do you have a soil test to promote this? So again, we don't want to just go out there and start doing lime, because remember, depending on the lime that you use, you could be potentially changing the soil chemistry for a long, long time, years, and imagine if over time we keep putting lime applications down. We don't need to. We can really end up having an effect on that soil root zone for a long period of time. So again, if you remember earlier, we talked about calcitic versus dolomitic lime. Okay. And the reason I want to talk about these things is, do we lime or do we not lime? Again, many lawn care companies offer lime applications to their customers without soil testing. It's a cheap money app. They go out there, it's an easy sell a lot of times, but you could be doing more harm than good, because the pH, the pH might actually be okay. A lot of times when I look at soil tests up here, we could do with a little more calcium. Calcium isn't going to necessarily hurt anything when it comes to soil testing, but a lot of times a pH might be okay. So we don't want to necessarily lime. And in this case, where we might want to increase calcium, but we don't want to change the pH, you're going to want to use gypsum. The other benefit of gypsum is that it also brings some sulfate along. So that sulfate, again, is another secondary macronutrient to the plant. I am starting to see more sulfur deficiencies in the soil. Gypsum could be a great amendment. And I would almost say that if I were a lawn care company and I were trying to sell them something, rather than selling them a lime, it might actually be better to sell them a gypsum app, because again, the gypsum is going to help increase the calcium in the soil, but it's also going to bring sulfate into the picture too, which can help the grass as well as a secondary macronutrient. So, but what if the pH is too high? What do we do if the pH is too high? We're going to want to come in and do sulfur. Let me see here. I want to go back again here. So, calcium magnesium ratios. So let's go back to this a little bit when we were talking about dolomitic versus calcium or calcitic lime. So, we want to make sure when we look at that soil test, typically on your base saturation section on a soil test, we want to see calcium in the 65 to 75% range. We want to see magnesium in a 10 to 15% range. We want to see potassium in a 3 to 6% range. Usually if you're testing, you're going to see hydrogen on there. Hydrogen is usually going to be less than 10%. Sodium, we want to see less than 1%. When we look at calcitic versus dolomitic lime is going to have magnesium in it. Calcitic lime does not have magnesium in it. So, keeping this in mind when we look at a test, if we already have adequate magnesium and we don't have adequate calcium, you're not going to want to use a dolomitic lime, because that's just going to increase our magnesium numbers further, and that's going to create some problems in the soil. Again, we don't want to have that too high. In the case where magnesium is adequate and calcium is not, pH is low, you're going to want to use a calcitic lime to go in there and raise that pH without affecting magnesium. If magnesium was low and pH was low, then we can obviously go in there and use a dolomitic lime. So that's why I don't typically recommend using dolomitic limes up here too much. So again, when we talk about pH being too high, now we're talking about getting in the sulfur. And it's usually going to come in two forms. It's either going to be a granular or a sprayable form. Most often we use a granular form of sulfur. But we can also use a compound, a fertilizer called ammonium sulfate. Again, it doesn't have a profound impact on pH, but it can slightly lower pH. If our pH isn't too off, we may be able to get away with just coming in there and periodically using ammonium sulfate applications. Another way that we can lower pH, again, is organic matter. A lot of times organic matter, because it does have weak organic acids in it, humic acids and fulvic acids and things like that, other organic acids and compounds in there. We can slightly lower pH with the incorporation of organic matter. We can also use fertilizers that contain sulfur, either in the sulfur coating, or maybe they also have sulfur in there, or ammonium sulfate containing fertilizers. Okay. So again, when we talk about base saturation, this is the amount of CEC battery that's filled with these base cations. So, again, CEC is going to vary with different soils. So when we talk about different soil types and what the CEC looks like, that's going to be how big or small our battery is. The base saturation is going to tell us how much of that battery, what percentage of that battery is tied up. So the way that we calculate that is we take the total base saturation, okay, which is going to be your, all of your main, cations, and then you divide it by the CC. So the largest ones are going to be calcium, magnesium, potassium, and sodium. So typically on a base saturation, that's what you're going to see. You might see some hydrogen on there if it's a more acidic soil, but we generally don't see that too much up here. Again, ideally, the ratio should be approximately 65 to 80% calcium to 10 to 20% magnesium. And the reason we want that is it's going to improve the bulk density and the availability of soil to resist compaction. If the magnesium ends up being too high, what ends up happening is these soils tend to become very soupy and sticky. If any of you guys have ever played baseball or softball, this could be real common too if you're out on that ball diamond, that skin. If you've ever had it, get to, basically chunk out on you. Sometimes this can be because there's too much magnesium present in that situation. So, again, like I was mentioning earlier ago, to lime or not to lime, if the magnesium is low and the pH is low, we want to use that dolomitic lime. Again, we're trying to keep those ratios in that 10 to 20% for magnesium and, 75 to, better on the magnesium. So, if we're already there with magnesium, if the magnesium's already, pushing 20%, we don't want to go in there and add more magnesium to the picture in the form of dolomitic lime. So if the magnesium is normal to high and the pH is low, we're going to want to use a calcitic lime in that situation. If the calcium is low and you don't want to affect pH, so let's just say your pH is in that 6.5 to 7 or maybe 7.2 range, so we don't really want to raise that pH, but the magnesium is too high and we don't have enough calcium on the base saturation, then, that's a situation where we're going to want to use gypsum. Gypsum is calcium sulfate. So it's contributing calcium, but it's balanced out. You have the calcium balanced out with the sulfate, so it's not going to raise pH. It's going to have a net neutral effect on the pH of the soil, but it's a way that we can get that calcium up in a soil without raising the pH. Okay? So soil organic matter percentage. This isn't always on soil tests. A lot of times you've got to pay extra to get this result. So this is going to be telling you the amount of active organic matter or detritus in the soil. And the other form of organic matter is going to be what we call stable organic matter or humus. So basically you have active organic matter, so this would be the part that's actively involved in chemical and metabolic processes in the soil, and then we have our stable or humus, stable organic matter, which is the base foundation. So ultimately, when you have organic matter being incorporated in the soil, it's going to go through a bunch of processes, metabolic and chemical processes in that soil. Ultimately, what happens is over time, it's going to polymerize, and you're going to, polymerize would be basically that they're going to start reacting and ganging up with each other and forming bigger and bigger molecules in the soil. And over time, those polymers are going to condense into the form of humic material in the soil. All right, so the other form of organic matter in the soil is in the form of microorganisms, okay? All soil has some amount of soil organic matter. There's there really isn't a situation where you have soils that are completely devoid of organic matter. They're all going to have soil organic matter in the form of either active organic matter, humic substances, or microorganisms. So the easiest way to visually tell is by how dark the soil appears. So when you look here, in the root zone especially, you can see how dark the root zone looks in this profile. So, this is a really good indicator of how much organic matter is in the soil. This is a great time of year if you're driving out in the country, if they plowed the fields. If you drive, you can see variations in the color of that soil. You might see lighter areas and darker areas in the soil. That's a really, really good indicator of how much organic matter is present in that field. Our soils up here in Northeast Ohio typically have about 1 to 2% soil organic matter. So that's not uncommon to see. It's not a particularly high number, but it's a pretty normal number, and it's adequate. For our soils, it's adequate. It's considered decent. Soil organic matter, 1 to 2%. If we can get more, if we could get it up into that 4 to 5% range, that would be even better. But 1 to 2% soil organic matter is going to be adequate, when we're talking about our soils. The other thing that we want to talk about again, and we've talked about this in a few other sections, is soil texture. Your soil texture, which is going to be the amount of sand, silt, and clay in a given soil, it's going to have an impact on your soil bulk density. It's going to impact, if you have compaction, that soil bulk density, you're going to have a critical threshold for plants to be able to grow. It basically helps us to better understand structurally what's going on in soil. So, we have the soil chemistry component of the soil test, but then we also have the physical component, which is going to help us, again, better understand what's going on in that soil. All right. Not every problem that occurs in a lawn situation can be traced back to a pest or a nutrient deficit. Okay, so maybe you go out on this and you think a lawn is deficient, and you go do a soil analysis, and lo and behold, it comes back, everything looks normal, looks decent. There really isn't anything outlandish. Your pH is fine, your base saturation is fine. And you don't see any evidence of disease or insect, you could be dealing with a structural problem in that soil, such as compaction. So again, this would be another picture showing that, otherwise the plants, look pretty green and healthy. So, we know that there isn't a nutrient deficit. We know that there isn't something else going on here. So, in this case, this is basically a structural problem where that soil structurally cannot support the growth of and health of those plants. So, soil structure is going to change depending on the texture and the bulk density of that soil. So, this is called the limiting growth factor. And so, basically, when we look at different soils and soil textures, we have different limiting growth factors based on the bulk density of soil. If we have a lack of pore space or porosity, we call that compaction. So basically compaction, when we talk about compacted soil, it basically means that we're driving out all of the pore space. And the pore space basically is where all the magic happens in the soil. This is where all the chemical exchanges are going on. This is where the microbes live. This is where the roots grow. The roots are growing through this pore space. This is also basically, what's holding all of the water and everything else that's important in the soil. So if we start compacting the soil, whether through mechanical processes from too much foot traffic or wear traffic, whatever, or, maybe we have a drought and it causes the soil to collapse and compact, or maybe we end up having too much soil or too much sodium entering into that soil through de-icing salts and things like that. We can actually increase compaction in that soil. So it isn't necessarily always the result of maybe, too much play on a field, or, too much equipment driving over an area, or too much foot traffic. I mean, those all can cause compaction, but there's also other chemical and environmental things that can cause compaction to occur. So just keep that in mind. So when we talk about bulk density, basically what we're doing is we're taking a sample of a known volume and we're drying it and we're weighing it. Okay. The other way that we can kind of get an idea, at least of compaction, is by using a penetrometer. It's not going to give us a true bulk density reading, but it can help us to gauge how compacted a soil is. Soil texture and bulk density, again, are going to affect water storage and infiltration. One of the ways, and we did this earlier on, that we can check for soil texture is with a jar test. Again, we can determine the soil texture with a jar test. That's a pretty good way of determining it. And then if we need to, we can take a bulk density reading of that soil, and then if you compare it, if we use the soil texture analysis and then we figure out the bulk density, we can again use this and look at the limiting growth factor based on your soil type pyramid, and use it to determine whether or not that soil, is too compacted, or if it's adequate for growing plants. So again, not every problem that we have in soil can be traced back to some sort of nutrient issue or other environmental factors. Sometimes it is a structural or mechanical problem of the soil, and it's something that you want to be aware of. And, ultimately, one of the best ways to start, again, is doing that jar test on a soil to figure out what soil texture you're dealing with to begin with. That will really help you to understand a lot when you're looking at the soil and CECs and things like that. So what are some of the takeaways when we look at soil testing up here in Northeast Ohio? What are some of the takeaways that we can look at? So number one, don't assume anything in soils in Northeast Ohio. When you look at a soil map, or geological map of Ohio, you can see that, up in the Northeast Ohio especially, it can be very diverse depending on where you are. So you can't take anything for granted that we're all just one way or another. If you were over in Toledo or Northwest Ohio, you could get away with that. But it can be a little challenging up here in Northeast Ohio. We have different bedrock formations under Northeast Ohio, and these different bedrock formations are going to lead to differences in soil texture and chemistry. For example, we have a lot of lake ridges that have high sand content. Soils can be very different from one side of the lake ridge to the other side of the lake ridge, okay? We have pockets of more acidic and highly organic soil left over from bogs and kettle hole formations. A couple areas where you see these. If you know Lake Isaac and Lake Abrams over in the Middleburg Heights area, those are actually called glacial kettle holes. So those are the remnants where large sections of glacial ice basically were left behind as the glaciers retreated and melted away, and it left kind of this low area where over time a lot of organic matter accumulated in these low bog type areas, and it forms what's called a kettle hole. Another one would be Chippewa Lake down in Medina County. That's another, basically that entire lake is the remnant of a kettle hole formation when the glaciers retreated. So some of these areas where you get in and around these kettle hole formations could be very acidic, but they also are very, very rich in organic matter. We tend to see a lot of silty clay soils closer to Lake Erie. So as you're moving further north in the soil profiles toward Lake Erie, we tend to see that. We also tend to see soils higher in magnesium. but they're deficient in phosphorus, boron, zinc, sulfur, and magnesium. So, that's something that we run into when we run into these silty clay soils in northeast Ohio. Soil pH could be very extremely variable too. But general rule of thumb is it tends to increase in acidity as we move from west to east. So when you're out west, when you're out places like north central Ohio, around Fremont, Sandusky, Norwalk, places like that, those tend to be more limestone based soils. As you move further east, into the Allegheny Plateau. You're moving into more shale and sandstone formations. So generally, as we're moving further eastward, we're also moving out of the areas of glaciation and moving into more unglaciated soils that are much older and much more aged. So they haven't been disturbed as much. So, again, general rule of thumb is we move from west to east towards Pennsylvania, you're going to be decreasing soil pH as we move from west to east. You also don't want to overlook the benefits of cultural maintenance practices to fix problems. So again, don't always assume that there's some soil issue going on. A lot of times you get in there and your soil texture looks decent, organic matter's decent, pH is decent, soil nutrients are adequate. So, if everything looks great on that front, then something else has got to be going on. And so you don't want to overlook the benefits of cultural maintenance practices to fix these problems. So a lot of times what ends up happening is, a customer could call and they want a silver bullet, some sort of magic pill or product, something potion that you can throw down that's going to fix the problem. That's not always the case. A lot of times we want to, look for a quick fix and it isn't. Sometimes we have to get in there. Maybe the thatch layer is too much. Maybe it's just the wrong type of grass for the site. And we do all the testing and we're like, look, you have great soil and you have adequate nutrition. Everything looks great. I think your grass just sucks. Maybe we want to come in here and replace it with a better grass. Okay. Or maybe we want to get in here and dethatch, or we want to aerate to get rid of some of that thatch layer that's built up. So, okay. Well, we are here. We finally got through and finished module 9. And, again, like I always say, I know I'm trying to jam through this because we're running out of time here this semester with this class. So if there's anything that you want me to, clarify or, elaborate on, please don't hesitate to reach out to me. And, and I'll be more than happy to follow up with you on this. So,